Our planet wasn't always the blue oasis we know today. Around 4.5 billion years ago, Earth formed from a swirling disk of dust and gas orbiting the young sun. In its infancy, our world was a molten hellscape, bombarded by asteroids and comets in a violent era called the Late Heavy Bombardment. With surface temperatures hot enough to vaporize rock, any water present would have instantly turned to steam and escaped into space. So how did Earth go from a scorching wasteland to a planet 71% covered in water?
For years, astronomers believed Earth's water arrived after the planet had cooled, delivered by icy comets from the outer solar system. These frozen wanderers, often called dirty snowballs, seemed like perfect candidates, packed with ice that could melt upon impact, filling young Earth's basins with life-giving water. But when scientists began analyzing the chemical fingerprints of comet water, they hit a snag. The ratio of deuterium, a heavy form of hydrogen, in comet ice didn't match the water in Earth's oceans. If comets were the main source, our oceans should have a different chemical signature. This discovery forced researchers to look elsewhere for Earth's water, and they found a surprising alternative: asteroids. Not all asteroids are dry, rocky bodies. A special class called carbonaceous chondrites contains surprising amounts of water locked within their minerals. Even more compelling, the deuterium ratio in these asteroids matches Earth's oceans almost perfectly. This revelation turned planetary science on its head, suggesting that while comets may have contributed some water, the bulk likely came from asteroids that bombarded Earth during its fiery youth. The Late Heavy Bombardment, a period of intense asteroid impacts between 4.1 and 3.8 billion years ago, may have been the critical delivery event that filled Earth's early basins with water. But the story doesn't end there. Recent research suggests Earth might have been wetter from the start than we ever imagined. Some scientists now believe water was present in Earth's building blocks from the very beginning, trapped within the minerals that formed our planet. As Earth's interior cooled and solidified, this ancient water was gradually released through volcanic outgassing, creating the first thick, steamy atmosphere. Over millions of years, as temperatures dropped further, this vapor condensed into rain, torrential downpours that may have lasted for millennia, slowly filling the low-lying basins that would become our first oceans. This theory paints a picture of a planet that never truly lacked water, but instead cycled it between its interior and surface over billions of years. The mystery of Earth's water extends far beyond our planet. The same processes that delivered water to Earth may have played out across the solar system, leaving traces on worlds we once thought were bone dry. From the icy plumes of Saturn's moon Enceladus to the vast subsurface oceans of Jupiter's Europa, water appears to be far more common in our cosmic neighborhood than we ever imagined. These distant worlds, frozen in time, may hold clues not just to how Earth got its water, but to how life itself began in the primordial soup of our young planet. As we continue to explore these alien oceans, we edge closer to answering one of humanity's oldest questions. Are we alone in the universe, or is water, the elixir of life, as common as the stars themselves? The journey of water to Earth is intertwined with the chaotic early history of our solar system. As the young sun blazed to life, it created a swirling protoplanetary disk of gas and dust where planets were beginning to take shape. In these turbulent conditions, water molecules could only survive in the colder outer regions of the disk, beyond what scientists call the frost line, a boundary where temperatures were low enough for water to exist as ice. This explains why the inner planets, like Mercury, Venus, and Mars, formed relatively dry, while the outer planets and their moons became reservoirs of frozen water. Earth, sitting in a precarious middle ground, somehow managed to acquire and retain enough water to become the life-bearing world we know today. The process of water delivery to Earth was likely a complex interplay of different mechanisms. While asteroid impacts provided much of our water, recent studies suggest another fascinating possibility: that water vapor could have been directly absorbed by Earth's growing mantle from the surrounding nebula. This means some of Earth's water might have been present during the planet's formation, trapped within the very rocks that built our world. Additionally, the solar wind, the constant stream of charged particles from the sun, may have contributed by interacting with oxygen-rich minerals on asteroid surfaces, creating water molecules that later hitched a ride to Earth on these space rocks. The timing of Earth's water arrival is equally crucial to understanding our planet's evolution. Evidence from ancient zircon crystals in Western Australia, some dating back 4.4 billion years, suggests liquid water existed on Earth's surface remarkably early in its history. This challenges previous assumptions about how quickly Earth cooled and developed stable bodies of water. These microscopic time capsules tell us that oceans may have formed just a few 100 million years after Earth itself, creating the stage where life's drama would eventually unfold. The presence of water so early implies that the delivery process was not just a single event, but rather a continuous reign of water-bearing objects over hundreds of millions of years. Mars tells a cautionary tale in this cosmic water story. The red planet shows clear evidence of ancient river valleys and lake beds, proving it once had liquid water on its surface. But unlike Earth, Mars was too small to maintain its water over geological timescales. Its weaker gravity couldn't hold on to an atmosphere thick enough to keep water liquid. And without plate tectonics to recycle water and minerals, Mars gradually became the arid world we see today. This stark contrast highlights how Earth's size, magnetic field, and geological activity made all the difference in preserving its precious water resources. Looking beyond our solar system, the discovery of water vapor in protoplanetary disks around other stars suggests that Earth's watery history might be common across the galaxy. The Kepler Space Telescope has revealed numerous exoplanets in the habitable zones of their stars, where liquid water could theoretically exist. Some of these distant worlds may have undergone similar processes of water delivery and retention, raising tantalizing possibilities about the prevalence of life in the universe. As we continue to study how water came to Earth, we're not just uncovering our own origins, we're developing the tools to understand how common water-rich, potentially life-bearing planets might be throughout the cosmos. The story of Earth's water is still being written. Each new discovery, from analyses of asteroid samples returned by spacecraft to observations of distant planetary systems, adds another piece to this cosmic puzzle. What began as a mystery about our own planet's past has blossomed into a fundamental question about the nature of planetary formation everywhere. As we stand on the shores of our oceans, looking up at the stars, we're beginning to understand that the water that makes our world unique is actually part of a vast, interconnected cosmic cycle, one that may have given rise to life not just here, but perhaps on countless worlds throughout the universe. The presence of water on Earth set the stage for something even more remarkable: the emergence of life. The same water molecules that arrived via asteroids and comets became the medium in which the first organic compounds assembled, interacted, and eventually formed self-replicating molecules. Recent experiments have shown that the conditions around hydrothermal vents in Earth's early oceans could have facilitated the formation of amino acids and other building blocks of life. These deep-sea environments, protected from the harsh surface conditions of the young Earth, may have served as natural laboratories where chemistry gradually crossed the threshold into biology. The water that came from space didn't just fill our oceans, it became the fundamental matrix in which life first stirred. The water cycle we know today, evaporation, condensation, precipitation, is just the surface layer of a much deeper planetary process. Earth's plate tectonics continuously recycle water between the surface and the mantle, with subducting oceanic plates carrying water deep underground where it's stored in minerals. Volcanic activity then returns some of this water to the atmosphere, completing a cycle that has operated for billions of years. This geological water cycle helps regulate Earth's climate and may explain why our planet has maintained liquid water for so long, unlike our neighboring Venus, where a runaway greenhouse effect turned all water into atmospheric vapor. The interplay between Earth's water and its geology created the stable conditions necessary for life to not only emerge, but to thrive and diversify over eons. Modern technology is allowing us to trace Earth's water story with unprecedented precision. By analyzing the isotopic composition of water in ancient rocks, in deep mantle samples, and in cometary ices, scientists are building a detailed timeline of when and how water arrived on our planet. Space missions like Japan's Hayabusa 2 and NASA's OSIRIS-REx, which returned samples from asteroids Ryugu and Bennu, are revealing that these space rocks contain not just water, but also organic molecules. These findings strengthened the connection between water delivery and the origin of life, suggesting that the ingredients for biology might be common throughout the solar system. The more we learn, the more it appears that Earth's water story is part of a grand cosmic narrative of molecular exchange between stars, planets, and the space between them. As we look to the future, understanding Earth's water origins becomes crucial for our survival as a species. The same processes that brought water to Earth, asteroid and comet impacts, pose existential threats today. By studying how water was delivered, we gain insights into planetary defense strategies against potential impactors. Moreover, as we search for ways to sustain human civilization, knowledge of Earth's deep water cycles informs our understanding of freshwater resources and climate regulation. The story of Earth's water, spanning billions of years from interstellar space to the glass in your hand, reminds us that we are part of an ongoing cosmic process, one that began with the formation of our solar system and continues to shape our planet's future. Ultimately, the water that fills our oceans, falls as rain, and flows in our veins is more than just a chemical compound. It's a cosmic traveler, a geological sculptor, and the essential ingredient for life as we know it. Every drop contains within it the history of our solar system, from the cold molecular clouds where stars are born to the violent collisions that shaped our young planet. As we continue to explore our solar system and discover water in unexpected places, beneath the icy shells of moons, in the shadows of lunar craters, and in the atmospheres of distant exoplanets, we come to appreciate that Earth's water is both ordinary and extraordinary. Ordinary in its ubiquity throughout the cosmos, yet extraordinary in how it transformed a rocky planet into a living world. The next chapters of this story will be written by future explorers who may find evidence of life elsewhere in our solar system, proving that the journey of water is indeed the journey of life itself. The story of Earth's water continues to unfold as we push the boundaries of exploration and scientific understanding. Recent discoveries have revealed that water exists in places we never imagined, trapped in the crystalline structure of minerals deep within Earth's mantle, suspended as vapor in the atmospheres of distant gas giants, and even embedded in the scorching surface rocks of Mercury. This ubiquity suggests that water is far more resilient and widespread in our solar system than we previously believed. The James Webb Space Telescope has detected water vapor in protoplanetary disks light years away, showing us that the same processes that brought water to Earth are likely occurring right now around countless other stars. Each new finding adds another layer to our understanding of how this simple molecule became the foundation for life on our planet. The chemistry of Earth's water holds clues to its extraordinary journey. When scientists examine the isotopic ratios of hydrogen and oxygen in different water samples, they can trace the water's history like detectives solving a cosmic mystery. The water in your body contains hydrogen atoms that have existed since the beginning of the universe, oxygen atoms forged in ancient stars, and a molecular structure shaped by billions of years of geological and biological activity. Some researchers have even found evidence that a small percentage of Earth's water may be older than the Sun itself, preserved from the interstellar medium that existed before our solar system formed. This means when you drink a glass of water, you're consuming molecules that have traveled across space and time, surviving supernovae, asteroid impacts, and the rise and fall of continents. The future of water on Earth is as fascinating as its past. As climate change alters precipitation patterns and sea levels rise, we're witnessing how delicate the balance of Earth's water systems truly is. Scientists are studying how ancient civilizations adapted to water scarcity and flooding, looking for lessons that could help us navigate the challenges ahead. Meanwhile, space agencies are developing technologies to extract water from lunar soil and Martian ice, recognizing that water will be the most precious resource for future space explorers. These efforts connect directly back to understanding how Earth got its water, because the same processes that delivered water here could help sustain human presence on other worlds. Perhaps most profound is how the study of Earth's water has changed our perspective on life in the universe. The discovery of extremophiles, organisms thriving in Earth's most inhospitable watery environments, has expanded our definition of habitable conditions. If life could emerge in Earth's early oceans, could it have also begun in the subsurface ocean of Europa or in the methane lakes of Titan? As we continue to explore these alien water worlds, we may find that Earth's relationship with water isn't unique, but rather one example of a universal pattern. The molecules that condensed on asteroids survived the violence of planetary formation and nurtured the first life on Earth, may have done the same on countless other worlds throughout the cosmos. Our search for water's origins has become a search for our place in the universe, and potentially for company in the cosmic ocean we all call home. The deeper we probe into Earth's watery origins, the more we realize how profoundly this single molecule has shaped our planet's destiny. Water didn't just passively accumulate on Earth. It actively transformed our world through a series of cascading effects. When enough water had collected to form persistent oceans, it began dissolving minerals from Earth's crust, creating the unique chemistry that would eventually support life. These primordial seas acted as giant reactors where simple molecules could concentrate and interact, while underwater volcanic vents provided both energy and mineral catalysts. The water cycle itself became Earth's first climate control system, regulating temperatures and weathering rocks to release nutrients. This dynamic interplay between water and rock set in motion the geological and chemical processes that made Earth habitable. Remarkably, Earth's water may have played a crucial role in developing the planet's magnetic field, our invisible shield against solar radiation. As water-bearing minerals were subducted deep into Earth's mantle, they altered the viscosity and flow patterns of molten rock in the outer core. These changes may have enhanced the geodynamo effect that generates our protective magnetic field. Without this shield, solar winds would have stripped away our atmosphere as they did on Mars, and life as we know it could never have evolved. Thus, the water delivered by asteroids didn't just fill our oceans, it may have helped create the very conditions necessary to keep that water from being lost to space. The story of Earth's water continues to evolve with cutting-edge research. Scientists are now using quantum mechanical calculations to model how water molecules behave under extreme pressures deep within Earth, revealing that our planet may hold several oceans worth of water locked in mantle minerals. Space missions to icy moons like Europa and Enceladus are showing us how water and rock interact in alien environments, providing new perspectives on Earth's own history. Meanwhile, astronomers are detecting water vapor in the atmospheres of exoplanets, allowing us to compare our water story with those unfolding around other stars. Each discovery reinforces the astonishing realization that the water in our bodies, our oceans, and our atmosphere is part of an immense cosmic cycle that predates our solar system. As we face global challenges like climate change and water scarcity, understanding Earth's water history becomes more than academic. It's essential for our survival. The same processes that brought water to Earth continue today, with tons of cosmic water still arriving annually via micrometeorites. While negligible compared to Earth's total water volume, this constant rain reminds us that our planet remains connected to the wider solar system. Looking ahead, humanity's expansion into space will depend on our ability to locate and utilize water resources on other worlds, making the lessons from Earth's watery past crucial for our future as a spacefaring civilization. The molecule that made our world unique in the solar system may ultimately become the key to leaving it. Ultimately, Earth's water represents one of the universe's most profound alchemies, the transformation of simple cosmic ingredients into the possibility of life. From interstellar clouds to planetary oceans, water has been both witness and participant in some of nature's grandest processes. As we continue to study its journey, we're not just uncovering our planet's history, we're learning how fragile and precious our watery world truly is in the vast expanse of space. The story of Earth's water, still being written after 4.5 billion years, remains humanity's most important story, because without it, none of our other stories would exist to be told.